Good morning again, Physics 30s. Working on the photoelectric effect part 2, Millikan's verification of Einstein's formula. All right, so remember we did the notes last page. So we're looking at question number 1 here in the practice set. So the minimum potential difference to stop photocurrent is 3.60 volts. What's the maximum speed of the photoelectrons as they leave the cathode? All right, the equation that we had on the previous page was EK max equals QV stop, because potential difference was used to be able to create energy to oppose fast moving electrons. And so we're looking at the maximum speed. So we're looking for V max in this kinetic energy term. So I'm going to go ahead and solve this for V max. First of all, substitute in what it is in terms of, right, variables for kinetic energy, and QV stop. V max, pardon me, where's my square? Is equal to 2q v stop divided by m and square root. Now the charge is the charge of an electron, and 3.60 volts, and m is the mass of an electron. And the calculation. All right, 1.12 E36. All right, let's take a look at another problem here. Question number 3. So we're looking at a Physics 30 student investigated the relationship between incident frequency and the resulting EK max of the photoelectrons. The results are shown in the graph. Oh, isn't that nice? The points are all plotted for us and everything. So it says here, using only the line of best fit, determine the threshold frequency, Planck's constant, and the work function. Okay, so let's grab a little ruler I can use to do this. There we go. So I notice these lie very nicely along a straight line. It's about there, pretty close to that. That's pretty good. All right, the threshold frequency. So frequencies along this axis, EK max, vertical axis. Pardon me. This would be our threshold frequency right there. Okay. So F sub naught should be roughly about, I don't know, they have here 5.8. I'll go with that. It looks like about 5.75. I kind of have this point a little bit skewed there, but 5.8 E14 hertz. For part B, Planck's constant. Well, Planck's constant should definitely be referred to, well, be directly related to the slope of the graph. So the slope of the graph is equal to Planck's constant, which is h. And so let's take a look at reading some points off the graph. And so I'll just use my ruler here to try and guide my eye a bit and pick a point that looks like it's perfectly on there, which should be right around here. Okay. And so down below, corresponding with that point, we've got that location there. All right, so I've got my one coordinate point here, which is 11.5 E14, and vertically it was 3.8. Okay, now let's grab another point that's on the graph in a fairly nice, easy to read spot. How about right there? And right here. Okay, draw the line all the way across if you want. I'm just trying to pick those points off right here and here. All right, so that's about 7.5 E14 and 1.2. All right, so what do we have here? What's the rise and what's the run? Well, the rise should be 3.8 minus 1.2, and this should be E negative 19, because that's what we have here on the vertical axis. Okay. Now the horizontal axis, we want to use the, I guess I didn't put I didn't put the power of 10 there. I did that for this part, but oh well, sorry. And then we have 11.5 E14, take away 7.5 E14. Okay, so the calculation, 3.8 E negative 19, take away 1.2 E negative 19, divide that by, open bracket, 11.5 E14, take away 7.5 E14. 6.5 E negative 34, they got 6.7, so that's pretty close. And the last part here, it says here the work function. Well, the work function is H times F sub naught, and so in this case here, we're going to use the calculated value, 6.5 E negative 34, times the threshold frequency, which we got about as 5.8 E14. And I get about 3.8 E negative 19. This would be in joules. I should actually put this in joules seconds. I didn't put my units there for that one. Sorry about that. Okay, that does a couple of questions there in this section. Let's take a look at one more. Let's do question number 5. Okay. The maximum wavelength to emit photoelectrons from a metal is 565 nanometers. If the incident photons have 6.70 eV of energy, then what is the minimum back voltage to stop the photocurrent? Okay, so good question. So first of all, the way we work through a problem like this is we set up our basic equation for E photon, conservation of energy, is equal to EK max plus W. Okay, so that's the equation I've been writing time and time again in the last couple of lessons, or practice questions, I should say. So now what do I have here? Well, it says the maximum wavelength to emit photoelectrons. That refers to the work function. And the incident photons have this much energy, and so we have the energy of the photons. Now we want to figure out what EK max is. So EK max is energy of the photon, and then minus, well, instead of W here, I have the maximum wavelength, so it'd be HC over wavelength naught. Threshold wavelength. Now the calculation here, I want to have the calculation in joules. So the energy of the photon here is 6.70 eV, and I can calculate it in joules by just multiplying by 1.6 E negative 19 joules for every eV. Now minus H, we'll do 6.63 E negative 34 joules seconds times 3 E8 divided by that wavelength that's given there, 565 E negative 9. All right, let's do the calculation here. 6.63 exponent negative 34 times 3, oh, pardon me, 6.7 times, what was why I was doing that? T minus, there we go. Okay, 7.19965 E negative 19 joules. And from that, the minimum back voltage. Okay, so EK max equals QV stop. And so right now we can just calculate the stopping voltage by taking EK max and dividing it by Q. Just a little more space down here, and let's get that done. 7.19965 E negative 19 divided by 1.6 E negative 19, the charge of an electron. All right, 4.499. So again, 4.50 volts. All right, thank you for joining me with that.